Having a seminar and talking about recent work with Relational on the dressing method. Please.
Thank you. So today I will present, in fact, the results we have recently obtained on, let me call it, relational supersymmetry. In a broader sense, then I will, of course, go into the details of what I mean with this. Relational supersymmetry and unconventional supersymmetry via the dressing field method. So relational in the sense that by means of the dressing field method, which is a very precise mathematical prescription to extract the gauging variant physical degrees of freedom of a theory, and so the relational degrees of freedom. And what I mean with this, as we have already seen in journal seminar, I mean the physical relations, the degrees of freedom instantiated between the fields. And so this is done via dressing, we will see shortly how. And it can be applied in general to field theoretic frameworks and also to physics in general, taking relationality as a paradigm and the dressing field method as a tool to implement it. And in particular, it applies particularly well in a geometric setup and therefore in a bundled geometric framework or super bundled geometric framework. And then to supersymmetry, because in fact it applies, I will also give you some references now, first of all. So regarding the dressing field method, works by Jordan. In general, first in the very construction, so the mathematical construction of the method, the development of it, and some physical applications, and the application in a general relativistic framework to the case of diffeomorphism, so differ dressing, reduction of diffeomorphisms, and then to general relativistic gauge field theory, therefore in a generalization essentially of previous works, plus examples in this paper. So it is a Forschittler physics paper. I will give you the archive 2407-0403. And so here you will find the way in which the dressing field method is constructed for general relativistic gauge field theory and applied. First, in a very, describing the geometric setup in a field space as a bundle, so in a very formal way and abstract. And then the way in which it is applied to examples, field theoretic examples, to the case of, so the cases in which the field set that we consider is metric and scalar fields, or for instance, metric, scalar, and gauge potential for scalars, because we consider for simplicity 4 dimensions and a gauge potential. And then there are those work that I would want to focus on today, which are supersymmetry and unconventional supersymmetry, which are these two. This is already published. 4504379 on supersymmetry and dressing, and this one on unconventional supersymmetry. 1898.
Exactly.
Yes.
The first reference you wrote 94 is 24.
Yes. Okay. To this. Yes. Otherwise,
because
yes.
94 they had a different way of.
Yeah, I know. And the are different. I know. So yes, and regarding those will be the two main ones that I will focus on. First of all, I will give. So I will start with a super quick review of the dressing field method, just the key aspects that are necessary to understand it, and then I will implement it in a rather explicit way. So we will not need really the whole geometric background in which it develops a field space, and we will just focus on its application to supersymmetry and unconventional supersymmetry today. So I will show that in the dressing field method, the procedure is that you extract a dressing field from the field content of your theory. And this is important because if you add it by hand, it would be like cases in which it's an ad hoc dressing field, or cases in which it is introduced from the outside. You are actually changing your model, you are changing your field space. And so it has to be taken, typically the right procedure would be to take it from the physical step, from the fields of your, from the set of fields of your theory.
Physical fields or auxiliary?
Well, it can be also, yeah, in principle, auxiliary also, but again, auxiliary are introduced by hand.
Okay.
So the idea would be to start with a set of field and see what happens. Yeah, possibly if you manage to dress it, is good. Yeah. And so the point is that you have to find if there is a dressing field, you have to extract it, and we will see, the important thing is that it is not a gauge parameter, and it has to transform in a specific way on the gauge transformation for being called, for it to be called a dressing. So you extract it and then you perform a symmetry reduction mechanism. You dress essentially, and via this dressing you implement a coordinatization with respect to some dynamical variables. So with respect to the dressing. And therefore, in this way, you get what we call the relational. It has an interpretation in terms of relational variables. That is to say, if you want physical degrees of freedom or gauge invariant degrees of freedom. And then I will mention the fact that you, of course, when you have some gauge symmetry in your theory, you may reduce the whole symmetry group or just part of it, a subgroup. And in that case, you are left with some meaningful internal residual symmetries of the first and the second kind. That way, first kind, they are those that are residual because they are those that are left of the gauge group after dressing. So in the dressing field transforms under them, and the dressed field will still transform under that symmetry. They will not be invariant. And then of the second kind, we just they encode an ambiguity in the choice of the dressing that you have at your disposal in your theory, and you can also be finite discrete rules of symmetry. So these are, I will start from these just to give you the key ingredients for gauge field theory and dressing, things that are you already know, but just to pass through all of it. And then I will move to, so first supersymmetry, and so consider in particular, I will show explicitly what happened for the case of bridge supersymmetry. So for the Rarita-Schwinger, say, spinor-vector, and then for the case also of supergravity, it can be extended here, is a bit more delicate. Let's say we will have to introduce at least at this level a perturbative dressing and implement it for a simple case. And then I will discuss how we did already in part, and we plan then to extend it to superspace as a dressing superfield, so in exploiting the Fermionic approach, and then possibly to higher structure and so on. So, but first of all, I will focus on this case and then extend for what follows in that case to the supergravity case. And I will show how some, say, gauge fixing conditions that are commonly implemented at the level of supersymmetric field theory to extract the off-shell degrees of freedom that we expect to have for the Rarita-Schwinger field gravitino they are not gauge fixing, but they are actually dressing, self-dressing in particular of the Rarita-Schwinger field of gravitino. And in this way, those fields are, first of all, they are fundamental objects of the theory, and they will be, in a sense, relational objects. And so, actually, instances of the dressing field method. I will focus on two cases. The first will be the gamma trace constraint. It is actually the one that we are used to. And then also to the divergence free constraint that is applied to the gravitino. Usually this is not implemented directly as a gauge fix because it's harder to get it directly from a Lagrangian, but anyway, I will also discuss it in parallel and also show you the difference between the two. And so essentially what will happen is that via the dressing you write your would-be dressed fields and you ask for the gauge fixing condition that actually are functional constraint, functional dressing constraint to be solved explicitly in terms of the dressing field, and then you check that you are really dealing with a dressing field, otherwise it means that you are not dressing. Okay. Gauge fixing and dressing are different both under the mathematical and under the conceptual perspective. And I will, here we just mentioned some key aspects of this fact, and if you want details on this difference, you can see the paper that is actually a philosophy of physics paper, but it's very detailed also under this conceptual and mathematical perspective by Philip Verhoefer and Jordan. Recent also this one. And then lastly, if there is still time, I will show you as the same occurs at the level of unconventional supersymmetry, in which case what I want to show, there is a lot to say there, but the key point here is that the so-called matter ansatz of unconventional supersymmetry, so which the first, the original model of unconventional supersymmetry, so the ABZ model, other Spanor-Vector model, is based on this matter ansatz, and I will see that it is actually, also in this case, an instance of the dressing field method, and again it consists on the self-dressing of the fermionic one form that we have in the supergeometric framework underlying the theory, which is not, we don't have to think of it as a Rarita-Schwinger or gravitino, no, it's just, we will see that this is another setup. Okay. So for the moment, let me start by quickly, giving you some basics, so starting from symmetry reduction via dressing field method. And so first of all, some basics that we already know, but just to fix a bit of the notation. So big basics of gauge theory. So when we have a gauge theory, we say we have this gauge theory of a manifold, and dimensional manifold, or better on a region, you say, of this manifold. And the gauge theory is based on a gauge group H with associated algebra H math track. And so the object that we have in our theory, let's be general in this one, we can have one form gauge connection, so say A. So A mu takes mu. And then we can have matter fields. And those introduce, so we can say that this belongs to space of forms U, where V is a representation space via the vectorial space via rho, that is the representation from G and B. When we have these kind of fields, so let me denote them in this way. Then for the minimal coupling, we introduce a covariant derivative.
Sorry, Lucrezia, what is the omega you wrote?
It's just a space of form, space of fields of forms. It's just form. P a vector space for writing the representation that we have. I will now write in the way in which A and phi transform matter fields via representation. It's a gauge transformation. It's called
So phi is the gauge parameter. So is the
phi is a matter field. It's
okay,
just a formal way to write in abstract as to give all the content. Then I will be specific. So this is just the very.
So the field content of the theory is A and phi. Okay?
Yeah, it's just to give you the dressing, and then we will apply the two things that we are much more used to dealing with. So. Okay, so we introduced a prescription for the minimal coupling via the covariant derivative, which is d phi plus star A phi, and then the field strength also of the gauge field in this way. Then we have a gauge group, so from the very fact that we have a structure group for a binary or say a Lie group H, we can also introduce the gauge, the associated gauge group H in this way, that is made of elements, say gamma and theta, such that eta gamma is equal to gamma minus 1 eta gamma. And therefore we can also write the associated gauge, the algebra.
But the gauge, the curl H is different from the right.
This is the rigid and this is the
the
gauge one.
okay,
So
this is
this is the one we are interested in. And in fact, we write the gauge transformations in this way. So we have that A gauge transforms as A gamma is usual, gamma minus 1, A gamma plus gamma minus 1 d gamma. So we have homogeneous and inhomogeneous term. And the phi, so the matter field, the gauge transformation is controlled by the representation, and so it's rho gamma minus 1 phi. And if you wanted the infinitesimal level, that we will also deal with the infinitesimal transformation in particular for the supergravity case. So infinitesimally, we have that delta lambda A is the lambda infinitesimal gauge parameter, and delta lambda phi is minus 1 star lambda phi. And then
write the low star A. What is low star A? In the covariant derivative of phi.
yeah, it's the way in which I indicate the pullback and the push forward. So it's the push forward in this case, while with upper star indicate the pullback. It's just notational to write in the way in which the representation
So it's the
takes as
pullback of
entry.
H.
Yeah, well, okay, maybe.
No, well, sorry. In that case, it's just the linearization of the representation of the group. Is the rho
Yeah,
star is the
right.
representation of the
Right.
Lie algebra
Yeah.
on V, essentially.
So this is the one that maps this
Because
way.
Okay. So it's A.
Yeah. And also, yeah, here. Okay, well, yeah. And the same, therefore, that you can do on the field strands, and as we already know, on the field strands, on the covariant derivative, we write the gauge transformation. All of these are at the kinematical level, and I will always try to distinguish between kinematics and dynamics from now on. So these are the kinematical basis of gauge field theory, of gauge theory. At the dynamical level, of course, if we have in mind a Lagrangian description, that is what we have in mind in this case, we construct a Lagrangian, which is a functional of the field that we have in our model. And then we can, typically what we have is that the Lagrangian is quasi-invariant under the gauge symmetry. So it means that it transforms with a boundary term. So let me write it like directed transformation L gamma and A gamma by gamma is A phi plus a boundary term which is a function of itself of A phi and the parameter gamma with gamma in H. In such a way that the field equation I will denote just a functional expression in this way now for being abstract. In such a way that the field equations are covariant. Okay, I just mentioned also maybe the fact that in this setup, when we can denote a gauge fixing, which means taking a slice of a submanifold of our field space, and so we can denote it as a constraint on the field of our theory that has to be satisfied. So in that case, a gauge fixing would be something like, say, a constraint on a gamma by gamma to be satisfied, and it corresponds to choosing a local section at the level of the boundary. I will show in a while, just in a very schematic way, how it differs from the dressing. Regarding the dressing, so I cancel here. It's invariant under cancellation of the variety. Okay. So dressing field method, again kinematics and then dynamics. So first of all, we can consider a subgroup kappa of H, K of H, and therefore a gauge subgroup of H. And we consider a kappa dressing field, a K dressing field, an object, let me call it U in general, then we will see the explicit case in supersymmetry and unconventional supersymmetry, that has to transform. The important thing is that it has to transform in this way under the action of K in kappa. And importantly, U does not belong to K, meaning that it is not a gauge parameter, it is a field, obviously. And then, once we manage from a theory to extract this a field that transforms, yeah.
Could it be in the adjoint representation of K, like free strength, for example?
Free strength, no, it has to be, no, it cannot be. It has to transform precisely in this way, and free strengths are
so not as a the adjoint representation of the group.
Because K can be, so which representation is K? Where you like K minus 1?
In the final case.
U is group value.
Yeah,
U
sorry,
is group value.
okay. Actually, to write it better should be like this, that you consider, you have two possibilities, say, either is. Let me introduce just this notation for a moment. Because U is group value, it has to be a map from M to G. So it is a group value actually field.
Okay, so this is the left translation.
Yep.
Yeah.
This is another.
Yeah. At the finite level is right as a left it has on the left.
Sorry, I don't understand that. You say in the first line that H contains G. And then that G contains H.
Yeah, because depending on the cases, yeah, you have two different cases.
Okay, now you are considering the
because,
first one.
yeah,
Okay,
exactly.
sorry.
Yes. Yeah. These again at finite level, and we will see
Okay.
how to apply it but yes. And well, yeah.
So G is a bigger, no, it's a smaller.
Yeah, it depends on how you manage to extract the dressing field.
But
So,
before you also mentioned that this field should belong to the set of fields of your original theory. So it should
yes,
be
should
part
even
of A, comma 5.
part of, yes, meaning that it has to be extracted from their degrees of freedom. Part of, we will see this for supersymmetry, for instance. To do this, you have to use some either irreducible or reducible representation. In this case, it will be actually reducible, and you extract fields, degrees of freedom from those.
With
Yeah.
certain combination.
Or certain combination, yeah, exactly.
But you can extract this U before implementing other constraints like age fixing. Because
you actually, well, okay, the way of applying depends.
we have to find a field that is valid only on a subgroup.
Yeah, you have to have it, check it.
Without
check it,
implementing
that way.
external constraint.
Yeah,
Like-
exactly.
It's
And
not
then
trivial to find-
once
It's not trivial to find in a theory.
it's not, yeah, you have, okay, yes.
The loop.
Yeah, yeah.
Like
So
loop
typically,
value.
in fact, we see that there is something that transforms in this way, or objects that are written in such a way that it resemble a dressing from the way in which they transform there. And then you say, okay, let's see if it really is a dressing. So you check if the constraint is fulfilled, it can be solved explicitly in terms of the dressing. And of course, that you have either if you are at finite level or infinitesimal level, that the dressing field transform properly to be as such, yeah. And to reduce the symmetry, actually, this is crucial precisely for the symmetry reduction, as we will see. So, and
An example of an inference that occurs to me is the cosset representative, no? In a supergravity,
you
the cosset
yeah,
representative
definitely.
is
Or
a field, can be viewed as a field which is
exactly.
good value
Yeah, exactly.
and transforms like that.
Yeah, in fact, yes. Typically, it's not said to be so, but all, in fact, we would want to.
Yeah, so
talk
supergravity
about
does
this
have an
other way.
object like that.
Yeah, they frequently occur, but they are not typically recognized as such, which is a pity both under the geometric perspective and also under the interpretative perspective, because it's strong under both aspects. And so once we have, if we manage to extract a dressing field, then we can dress the field of the theory. And so let me write dress the field. So we have our fields were A phi. They will be now dressed, so we will have say A U phi U. Let me just denote them this way now to be schematic again. So we will have that AU is defined as U minus 1 AU plus U minus 1 DU, and phi U dressed will be U minus 1 phi. And it will be K invariant, gauge invariant under the symmetry that has been reduced. And this is an instance in which we can see, well, at least in this case, and then more explicitly in other, that actually when you, so the dressing field is not an element of the gauge group, but the way in which you implemented the dressing, by the way in which the dressing field method was first formulated, once you have the difficult part is say extracting the dressing field, because then after you build the dressed object just by replacing with a rule of thumb. If you know how the gauge transform, you replace the gauge transformation, you replace the parameter in the gauge transformation with the field, with the dressing field.
What I do not understand in this level is, since the gauge parameter is anything which is in the gauge, which is a G valid, and so in which sense this looks very much like a gauge transformation. It is just exactly if you replace U with gamma, it is gauge transformation. How can what distinguishes U from a gauge parameter?
Yeah, the way in which it transforms on
Okay.
the gauge
Okay.
transformation, so the fact that it's a field.
Okay.
And so it is built with the physical degrees of
So
freedom.
it does not transform with the
Yeah, exactly.
okay.
And but it just so happened that at the field theoretic level, when you dress the field, you can use it as a rule of thumb to extract the dress from this replacement. But they are different objects.
Concretely,
Yeah.
if to have this transformation, the adjoint transformation of A
Yeah.
into a U,
That you have.
if this would be gamma, this would be associated to the fact that the U is in the adjoint representation, in the sense that it transforms with transform A with both indices. On the other hand, this kind of transformation is more typical of. How do you manage when you write it with indices, please?
But we will do it.
Okay.
Now,
Okay.
no, this is just, I know that I'm being asked
Because
to
it's
separate, but.
Well,
let me
one
just-
example we can give immediately, if you like, if you think, take A to be the spin connection, so it has
Okay.
Lorentz index,
Yeah.
and U being the tetrad field,
When you do.
which has the tetrad field, the Vierbein, right? We have a Lorentz index and a Ward index. The AU becomes the gamma, the
Okay.
Christoffel symbol, and it is of course a Lorentz singlet. It doesn't.
Yeah, essentially, yeah. Sorry. Written in this way should be, okay, it depends in which direction you go. But if the
Okay,
omega u is the gamma,
Yeah.
it is, okay, this will be gamma and this omega. And of course, yeah, sorry. So essentially it's like writing omega A d mu in terms of the crystal.
But in the case of the Vierbein,
Yeah.
there is an extra ingredient in the sense that you are changing the description from a gauge field of Lorentz, SO13, so what is, into a GL
Exactly.
transforming quantity, which is the gamma. So there is extra information. So it is necessary to have for it not to be a gauge parameter, it is necessary to have another gauge or another group which is involved or not.
Yes, you have the representation. Yeah, okay. The group theoretic level, of course, you will have the gauge group and like SO13, I don't know, and GR, yes, sure. But for better understanding this, you always have to think of, in this case, for instance, of Cartan geometric framework, in which recall that we are addressing what you are doing. That is also a difference between a gauge fixing and addressing. You think of the field space as a bundle or Cartan bundle, and of space or many for them. And so in the moment, so let's take this as a region. In the moments in which you do a gauge fixing, you're fixing a section here. With the dressing, you are actually, via pullback, you are projecting, it's like really a projection to an equivalence class by U, say. On n, and this is the difference. This is omega here and gamma lambda mu.
So you are substantially reducing Poincaré.
Yeah, you are reducing your killing
Lorentz.
Lorentz. Yes, you are killing Lorentz. And in fact, this is also something that we were discussing with Nelson. There are cases in which it seems non-trivial, theories for which it seems non-trivial to reduce completely Lorentz. So there are things that you can do. But yes, the idea is that you don't see Lorentz anymore in the moment in which you are changing mu and gamma lambda mu. So yeah.
In the definition of AU, the U appearing there is U or UK?
Here I'm thinking of UK. Okay, this is another point in the sense. UK you mean the transform one? No, it's U. It's U. Yeah, it's U when done in transform. So, and this object will be K invariant because I'm using a K dressing field to dress it. If you use a dressing field that transform under the whole, let's call it H, the whole H group, like so H is H minus 1U, then you will have reduced the whole symmetry group, and you will not have receiver symmetry of the first kind, but you might have, and probably in fact you have receiver symmetry of the second kind.
Which is the GL, precisely.
Which is the GL, exactly. This is one of the second kinetic ones, yes. Yeah.
So here, A transform in the joint, okay?
Yeah,
A, without
the
you.
bare one, yes.
A transform like this.
AU is gauge invariant. A
But-
transform like this.
Yeah, no.
In the area,
To
yeah.
get A invariant with
Yeah.
respect to that definition
Yeah.
should be in the joint.
Yeah.
Okay.
And okay, so that was more or less everything, but the fact that okay, something that is needed is also the perturbative dressing. So let me just maybe write it here. So perturbative dressing, which is of course you will have gauge invariance at first order, of course, when you dress perturbatively. And so let me take, for instance, you will consider those gauge transformation for the field, and then you will have that, so let me call nu the perturbative dressing field, so it will map from N to math frac G, so the algebra associated with G, and it will be such that delta lambda nu is minus lambda. So this is just the perturbative version, the infinitesimal version of finite gauge transformation. And then in the same way, it will be, so you will consider those gauge transformations at the infinitesimal level, replace the rule with the rule of thumb that the parameter will addressing, knowing that there are different objects, but it is still implementing this rule, obtaining the perturbatively dressed objects, and also the fact that
yeah. Is perturbative. Is the perturbative dressing.
Yeah, exactly.
Perturbative means that it's
Linear.
it's small, so it's close to something. So is it close to the identity element of G?
You can write an expansion in terms of, you can write expansions and taking only the first order terms. And so for instance, if you write the fields, you will have like, for instance, for scalar fields, you will have identities, the scalar plus perturbation of it, and then you dress it, you will have so combination of these objects and phi, and just in the dress way, and those elements, those in the perturbative expansion, those elements that are not at first order, so at second order, in the field and parameter, you will just neglect them.
So
What's the zero? I think his question is what's the zeroth order?
yeah, I mean this G that you wrote is the algebra, right?
Yeah, so
Yes.
Okay.
Yeah.
That was my
Okay, so
that was my question. So nu is the algebra, and
yeah,
is the shift in the
the
algebra.
zero, the identity of the zero, okay, sorry.
And now
I
there's the
got it
exit.
now. Yeah, okay.
Okay.
Okay, and so, well, just for you to know that any field, this is a bunch of fields that now I consider. So once I dress them, this will be delta lambda phi, and then we can write it like plus delta lambda nu phi, which is delta lambda phi plus delta minus lambda because of this transformation phi, which is delta lambda phi minus delta lambda phi, which is 0. And so it's the way in which you will have been invariant object at the perturbative level. We will see the example of this for the
Lucrezia, maybe write what is phi nu, because it's what.
yes, okay. Yes, sure. Yeah. Well, phi nu is the dressed object, so
precisely.
I mean, in general, for again a boundary field, would be phi plus delta nu phi. Yeah. Just and then to check that for the dressed field, you have invariance. So you know how of course you have to consider the way in which your field transform, the way in which the dressing transformer do the dressing and check the invariance. Essentially, it's always the same.
Delta nu phi is minus nu times phi, right?
Delta lambda phi is minus lambda.
No, delta nu phi, the last delta
is the prescription depending on how they transform, because
Okay.
phi is how they gauge transform. Phi now is not the tiny phi, but
It's an
it's
element of the
general. No, it's the field. Yeah, it's a general field that you may dress.
Maybe
so.
give for A, for example.
Yes, okay. I mean, no, but okay, it's just that then you can take a phi like this, and with delta nu, for instance, delta nu A will be d nu, and delta nu phi will be minus rho star
I don't know.
phi.
Yeah, no, just because indeed it may be confusing between this phi.
Yeah, I know, okay.
No, that's why.
Because capital phi is in space, right? So,
Yeah.
okay.
Equals into mu minus 1. Okay, mu minus 1 times
Phi.
So Q is
And
1
this
plus
is
mu.
like this.
The valuation is minus mu phi. Like this.
Okay, and the same, just to mention, because this was the kinematics, just to mention for a moment the dynamics, because okay, this is relevant also in other contexts that you might be interested in. For you, is the fact that at the dynamical level, when we consider a Lagrangian and we dress it, we have seen before that typically in gauge field theory what happens is that the Lagrangian is quasi-invariant under gauge transformation, meaning that it transforms with a boundary term, or invariance up, famous invariance up to boundary term. And so at the dynamical level, you would have dynamical level, like the delta line L5, for instance. Let me call this in the infinitesimal case, so just because we are so used to this. So delta mi A pi lambda. And so when you do the dressing, so perturbatively dressed Lagrangian, but also in the finite case is similar, just not at the infinitesimal level. You will have that this is equal to A phi plus d beta A phi. So like this, let's rewrite it like this. And so the dressed Lagrangian differ from the bare one by a boundary term written as a functional of the fields of your theory and the dressing field. So actually just the fields of your theory, because this somehow has to be extracted from.
So beta is expressed in terms of the network charges, right? Associated with
This is the piece in which commonly you extract, you can extract because, when you write the variational principle from action, you have the field equation plus the network charges emerging from, as usual,
Is beta the
But
same?
this is just the dress,
So the beta is the same.
The functional expression is the same, yes.
Okay.
Exactly,
So
Yeah.
in L there is no mu, you disappear.
In principle, if you no new, you mean like in this
New,
new the field,
the
the
field,
dressing. Yeah, this is the bare one. This is the dress one in which you have dresses, so the entries of the functional expression are the dressed object. And because the fact that the gauge transformation, we know again also the level of the Lagrangian, you use the rule of thumb, so you consider Lagrangian to be typically quasi-invariant.
Yes.
And so you will have this functional expression for the boundary terms in which you replace the gauge parameter with the dressing.
Okay. So there's a starting point is giving a theory with fields that are A and phi. Principle.
Yes.
And mu is another field.
No, it has to be. It should be extracted from your degrees of freedom.
Okay. So
It's some components of A, or for complex scales like the modulus and phase. And so somehow
It's not an extra degree of freedom, I would say.
Yeah, it
It's-
should
it's a
not be.
functional of the
Otherwise,
original
if
field.
it's another Perez it's another kind of, yeah. Also, the relational interpretation is a bit it's spoiled if you introduce it from the
But
outside.
in both cases, you should write in the end U as being U
Of
bracket of
phi.
A and phi. Same for nu. They are functional of the original field in the good case.
Okay.
If it is not, it is just something that you add by hand and you are simply changing the field. So it's cheating, essentially.
Does this work the same for a finite edge with the U instead of no?
Yes, yes. It's just that here I was finishing with the
No, no,
so
yeah.
I wrote it, but yes, absolutely.
So in some sense, nu is inside A and phi.
Yeah, but we will see now an example precisely to see better what it means to be inside a field. So.
Okay.
And this occurs, for instance, if we take already rigid supersymmetry and we consider the Rarita-Schwinger field. In the Rarita-Schwinger spinor-vector, actually, let me write it like psi alpha mu, just to write it explicitly in this moment, space-time and spinorial indices. What I'm going to show you works in any dimension and also for any amount of supersymmetry. So because it's kinematical, it's just a construction that can be implemented and you will immediately see why and I will show you how. So this is what is typically called a spin-3R field. The point is that Rarita-Schwinger, in the first paper, they actually introduced a spinor tensor field, so with more indices and with some conditions that have to be fulfilled by this field. And then in a case, in a particular case, it reduces to this simplest case. And at the level of the Lagrangian that we commonly call the Rarita-Schwinger Lagrangian is not the one that is recovered in the limit in which we get the Rarita-Schwinger spinor field in the paper of Rarita-Schwinger. This is just for curiosity. So, but let's focus anyway on this, on what we call the Rarita-Schwinger. So, on this spinor vector, the Rarita-Schwinger Lagrangian is written like this. That we write it both with forms and at least in some moments for completeness in components. Epsilon rho sigma, psi bar mu, gamma pi gamma mu, d rho psi sigma. Where is gamma mu takes mu. And the Rarita-Schwinger term, the Rarita-Schwinger Lagrangian, is quasi-invariant under gauge transformation, and let me write at this stage both the finite and the infinitesimal transformation, just for having them in mind from now on. So under psi that goes into psi epsilon, written in this way, so the finite one, psi plus d epsilon, which is in component psi mu that goes in psi epsilon mu, this is psi mu plus d mu epsilon, and then the infinitesimal version, which will be useful in figure. The epsilon psi is equal to the epsilon, which in component is just the epsilon psi mu equal to d mu epsilon, with this curl epsilon, bar epsilon, say, the infinitesimal parameter, and this one, the finite one, okay? So now the idea, there are two observations to be made. That are that first of all, this object, if we count its components, so what we commonly call actually the degrees of freedom, the official degrees of freedom in this way, in 4 dimension n equal 1 for simplicity, they are 16. And which we may ask which kind of field of irreducible representation are contained in this object, which is 1 plus 0 times 1 half. So it has spin 3/2, spin 1/2, and spin 1/2 field inside. So, irreducible representation. This is at the level of the graphs. So, if we think of the degrees of freedom, we would expect something like 8, 4, 4 for this kind of field. Okay. Second thing is that when we count the off-shell degrees of freedom, what we call the off-shell degrees of freedom of psi, alpha, mu in 4 dimensions, we count them to be 12. Somehow we remove the gauge transformation of psi. And at the level of how we implemented this in the theory, and in the not only outside, I mean in the literature, in the supersymmetric literature, there are two main constraints that are called gauge fixing constraints that are, let's say, is the gamma traceless constraint on psi. Let me just omit the index alpha from now on. And B, the divergence free constraint. And we will now see how both of these can be actually obtained. There are instances of the dressing field method, of self-dressing of psi, and how actually when we look at the dynamical level, because it's also, there are also some affirmations, some sentences in the literature regarding the way in which those two conditions are related. And actually, in fact, they are. On shell, it is evident how in one case you can derive one from the other, and how rather choosing another gauge fixing, you get actually a weaker constraint on shell. So I will also mention this after. So at this level, we just would want to see how and why this is addressing and not a gauge fixing. So let me first start from this. Is also actually probably the case in which we are more interested in usually. And so to show explicitly which is the dressing field, how we dress what is the particularly useful is to exploit the trace decomposition, which is a reducible decomposition of the Rarita-Schwinger field. And so we write that psi alpha mu is equal to rho alpha mu plus gamma mu chi alpha. Here I'm restoring the spin indices just to show their feature of this field. So this chi alpha is a spin 1/2 field. And it is defined as to be precisely the gamma trace of this object. Now we should already have in mind what may happen. So, and dimensions, of course. Here we will focus again for main, but let me generate here. And the rho, the only characteristic that it has is the fact that it is rho, such that gamma mu, rho mu, has to be equal to 0, because all the trace of psi is here, the gamma trace of psi. And so notice that this is a spin 1/2 part, so it has to have 4 degrees of freedom. And so this object is not a spin 3/2 field only, it contains 8 degrees of freedom, plus 4 other degrees of freedom, which are taking into account the fact that this is not a longitudinal transverse.
But you say that gamma mu is 0 or is different from 0?
Is equal to
No,
zero.
sorry, it's equal, because there was a...
Okay, yeah,
sorry. Yeah, there was a transparency still, yeah. And so...
I'm sorry, repeat the last
Yeah, so from this we can infer that chi has 4 degrees of freedom, spin 1/2. This is a reducible representation. And in a row, in principle, we still have is a spin 3/2 and a spin 1/2 inside it, because it has still a longitudinal and a transverse part.
Okay, so you say you did the algebraic part, but you didn't say anything about the transformation.
No, not yet. Now I will. But yeah, this is just to show you the decomposition, to see how degrees of freedom are rearranged and what we are using to dress also.
But then there is the residual gauge or supersymmetry invariance of rho
Yeah.
with a
no.
parameter satisfying the diagram.
No, in the sense that, as we will now, supersymmetry is used to reduce the addressing, the supersymmetric parameter addressing field, now we will see, is reduced. But yes, you have all the residual symmetries that are left, so Lorentz, U1, and whatever other symmetry, those, in particular rho, will still transform under those. Chi will disappear, we will see now why, because we already see that if this is something that we want to solve explicitly for the addressing field, the conditioner is going to take this as an entry, and we will see now. So,
so this is the gauge, what happens to the gauge field at this point? Namely, you
exactly.
kind of fix the Lorentz gauge, but then there is a residual gauge symmetry parameterized by a harmonic function that that you can use to fix more degrees of freedom. So you are able to.
Once, yeah, exactly. Also, actually, you don't check when you're framing that, because what will happen is that this constraint, when implemented, when you go on shell, because those are off shell-based kinematics.
Yeah.
When you go on shell, this will be, okay, 12, we will see now why it will go down to 12, but it will be 12 minus 4 because the field equation implies this. If we fix this, it will imply this. If we fix this, it does imply a weaker condition. We will also see this if we have time. And then you have the field equation and in fact the theory then we will be left with 2 degrees of freedom on shell, the one that you expect. Yeah. And this object will still transform under the residual symmetry that you have, whatever other symmetry you have besides supersymmetry in your theory. Unless you do addressing somehow, okay, not this, but some other addressing to reduce or bit, as we did in the GRGFT paper. So, here you have the transformation of psi.
Yeah, you will then, of course, you will explain better later, but I was thinking of, okay, supersymmetry transformation is the square root of diffeomorphism, of a translation, let's say, so in general.
In the sense Q, P,
yeah,
okay.
And so if you do twice a supersymmetry transformation, you get a translation with a special.
Yeah.
So when you address, okay, you are you do not see anymore this kind of diffeomorphic transformation of translation.
No, and besides
But we
that,
still have that supersymmetry. You still have it. The rho still transforms under the supersymmetry.
no, we will see that it will not. It will be invariant under supersymmetry. Under supersymmetry transformation, I mean those. It will be invariant. The dress, the row.
This one.
No, this one is not, it's bare. So yes, it transforms.
Okay. So
That
this
means, no, okay, row
okay.
transform. That we, okay.
Rho
Let's
transforms.
do like this. First, we take this.
Okay.
We see, we look at this transformation, we write the transformation for chi and for rho, because from the reducible composition you can write them. So first, let me write it. No, it's somewhere there. So I will not read it right, but just so for chi, there of course, so they transform, and it will be chi epsilon is equal to chi plus 1 over m. We can check that this is the case.
Yeah.
Where this is gamma t, okay? And the rho mu, we transform as the rho mu minus 1 over n gamma mu d slash epsilon plus d mu epsilon. And these are important actually to show also all the things, what is left after dressing and so on and so on. Those are the transformations just obtained from the reducible decomposition and the transformation, supersymmetric transformation of psi. Then we can now start implementing the dressing machine, the dressing method. So we define an object, psi u, dressed. So because in this, suppose in this moment we do not know if we have a dressing field and which is. in case. So let me define an object in this way. What we know is that if we have to dress psi reducing supersymmetry, it has to emulate, it will not be a superparameter, but it has to emulate that transformation. So we define it this way. Okay? And then we ask for the gauge fixing constraint to be explicitly solvable in terms of U for the dressed objects. In other words, we are now focusing on A, first case. So we ask for gamma mu psi u mu to be equal to 0. That is gamma mu psi mu plus d mu u equal to 0. And we try to solve it explicitly for u. And after this, of course, we have to check still that what we are obtaining is really a dressing field. So if it gauge transform as we expect, as we have seen before. So solving this explicitly, what we get is that this is solved by u written in terms of psi. So, and it is a field-dependent dressing field, because then I didn't mention before this, which was key actually, is the fact that what we are interested in, it was understood by my speech, but in essence what we are interested in is the field-dependent dressing field. So, and so this kind of object, in fact, which is minus the slash minus 1 gamma mu psi mu. And it is therefore, by definition, minus n d slash minus 1 chi. We check if it was a gauge transformation, it would not transform, but we check its gauge transformation, and what we get in fact is that it is precisely addressing. This is u psi epsilon, and it is in fact minus n d slash minus 1 chi epsilon. And this, okay, now we just go to replace the transformation of chi that we have here, we replace it here, and what you get is minus n d slash minus 1 chi minus epsilon, that is precisely u psi minus epsilon. And so in this case, for which we have in fact an additive abelian group, it is exactly what we expect for the dressing. So you can see then the details of it, but it's just what we expect. So the dressing field is now this. And we may observe immediately that it is a non-local dressing. And this means, and it's the details of this first analysis, you can find them in artificial versus substantial gauge symmetries by Jordan. It is the fact that if to reduce the symmetry, you introduce some non-locality, the symmetry, the gauge symmetry that you are reducing is said to be a substantial gauge symmetry of your theory. There are cases in which this does not happen, so you don't get a non-local quantity, and this is typically when the symmetry is artificial. For instance, the nearby symmetry in the Abis that model in 3 dimensions is precisely this kind of object. We will see this.
It's local.
It's
local?
it's artificial, ad hoc, it's another kind of thing. It's not as substantive as supersymmetry. In what case, actually?
So substantive means that once you fix it, you do some non-locality.
Exactly. Okay. Yes. And actually, okay, another thing is that once you dress and you get non-locality in the dressing, this doesn't mean that the action still will carry this non-locality. For instance, for mu, when you do the dressing with Dirac and mu, in that case, the non-locality is killed. Right.
It depends on which variable you want to write.
Yeah, it depends on the Lagrangian, of course, but it means it is not actually transmitted as a non-locality to the theory.
But in the case of a mu, it is still not local because.
In the case of a mu, the dressing
Yeah,
is
but
absolutely, yeah. And in fact, notice that this is analogous a bit to what happened for the axial gauge in 3D. So for when you do mu equals 0 with n a constant vector, and this is analogous to the d mu gauge fixing, which is again actually addressing in 3D again. So this is just an analogy. Of course, this is another thing, supersymmetry and so on, but just in spirit they are analogous. Okay, another important thing is that now that we have this.
Maybe to stress a fine point, that you've been super fast about this.
Yeah, I know.
But observing the fact that indeed the supersymmetry translation, it's an abelian group.
Yeah, so this is
So
why
in principle, if you take
yeah.
a gauge element, epsilon transformed by epsilon prime should be epsilon. So
Yeah,
if U was an element of the supersymmetry group of that model, it should not transform.
Yeah, I mean,
It should be a
if you were a gauge element, it would have been like epsilon equal U. But it is not, it transforms as we expect, so it is
Yeah, just to stress the fact, again, the clean,
transformations.
just to stress the clean mathematical distinction between a gauge group element and the dressing field, which in that case is manifest because it should be, in an abelian case, this guy should be, if it was really a group element, a gauge group element, it should be invariant.
Yeah. And so once you have, let me just take this now and see what is side dressed for completeness. We have we know the dressing field, we see that it is written in terms of chi. So we are somehow using the degrees of freedom carried by chi to reduce the symmetry. Let's see what happens. And therefore we have that we have the gauge invariant relational variables, physical degrees of freedom of psi u mu, it is, let me just separate it, plus d mu u psi, so the one that we have now obtained, we just replace it, and what we get is that psi mu minus n d mu d slash minus 1 chi, and it automatically satisfies the constraint, of course, that we have just written. So, and if we now look at the components, so the reducible components chi and rho, we can write their address the counterparties, either repeating the reducible decomposition for the dressed object or dressing the reducible items, say, field. And what we get is that chi u
So this coincides with the dressed rho.
Sorry?
Psi u mu coincides with the dressed rho.
Exactly, yeah, exactly. Because, and in fact, that is the point, precisely that chi dressed would be 1 over n d slash u psi. Again, rule of thumb, which is chi plus 1 over n time minus n d slash minus 1 chi, which is exactly equal to 0. So we have killed, say, chi by the addressing, or better, use its degrees of freedom to dress rather than kill. And so rho mu will be exactly this, minus n gamma mu d slash u psi plus d mu u psi. And this is exactly as Mario Weber is exactly psi u mu. And so we see that we have in fact of shell 16 minus 4 is equal to 12 degrees of freedom. So same, see, okay, we don't have a lot of time, I would still say at least some key things. So for the things that are simpler and more intuitive or that can be derived just following the prescription, let me just mention them and pass. Okay, so which is this. Regarding B, In the same way, you can show that this is also a dressing. For the Rarita-Schwinger field is an instance of the dressing. What you use is a decomposition into a transverse and a longitudinal psi. And you can see essentially that in the end, after all of this, you will have that psi u will be essentially psi transverse mu, and the longitudinal part will disappear. So this you can check it, but again it will be a non-local dressing, of course, and the procedure is just the same. You implement the dressing machine just using this decomposition rather than the trace, the gamma trace decomposition. At the level of the Lagrangian,
so in that case, you should find a different u.
yeah, exactly. It will be
Yeah,
kappa,
the same.
kappa is d mu, kappa, yes. You will, if you want, you can also write quickly u. That will be with u psi. It will be minus box minus 1, so non local again. The box is d mu, d mu psi mu. If we call, that is minus nabla, box minus 1 d mu psi longitudinal mu, and it is, okay, let me write it this way. It can still be written another way, but this is what you can immediately derive. Okay. Another thing that I want to mention regarding this is just at the Lagrangian level. So we take the Rarita-Schwinger Lagrangian that I written before. You dress it. We already know that you will have just the same functional expression, but with the dress field and a boundary term, which involves the dress field. Yes.
Regarding still the final line of case A, it's not clear to me that rho u is supersymmetry invariant. I mean, it still transforms under zero supersymmetry, right? Rho u.
Rho u does not transform. No, it is invariant and it automatically fulfills
That
the
does
resting,
fulfill that, but so it somehow transforms with the spin 3/2 component of the derivative of epsilon. Do you agree?
with, but the derivative of epsilon, so epsilon as a
So you
is a
take epsilon
gauge,
to be,
the supersymmetry gauge
you
parameter.
take the supersymmetry parameter satisfying the linear equation. So and
But
that
it's
is an
okay,
invariance.
but you are constraining the field to obey some equation. You have a constraint parameter in that case, so it's
You have a constraint on epsilon.
yeah.
There is a residual to supersymmetry.
If you have a constraint on epsilon, I don't know. So in this case, it's unconstrained gauge supersymmetry parameter. Doesn't have to obey any equation. So,
Okay.
in that case, okay, it might be that something different arises. So that
If
you
you-
have a reduced part, maybe, or yeah, that I don't know.
Because if you
Yeah,
just
yeah.
write it, transform u by epsilon, no?
Yeah.
Then u psi minus epsilon.
Yeah.
Then you see that there you have precisely a projector, we have projector of the epsilon somehow, right?
Yeah, I see. Okay, which
So-
in this term with unconstrained parameter, it is just a reducible or reducible decomposition that you are implementing. If you constrain the parameter, you may have things, different things happening. It's a different thing, but yeah, sure.
Okay.
Yeah. And anyway, say when you reduce some symmetry, some part of the gauge symmetry group, if you're doing it in a standard way with an unconstrained parameter, you will have the internal residual, the residual symmetries that remains of the first kind that are like here for this theory, maybe
Yes.
Lorentz, E1 if you have a gauge field and so on. Like you have, for instance, in unconventional supersymmetry. If you constrain the parameter, then something may happen more involved when you look at the decomposition of rho and so on. So yeah. but that's when we introduce constraint on the parameters. So at the dynamical level, the only thing that I mentioned before, and I will just mention it again, so is the fact that the Dresden Rarita-Schwinger will be the bare Rarita-Schwinger plus, so this is just the functional expression of the Rarita-Schwinger with U, so Dresden. This is the bare one that we have written before, plus the boundary term. The boundary term is the U bar, where U, depending on how we have dressed it, we have it now, wedge gamma 5 gamma deep psi. And now to observation is the fact that if we first fix A, the gamma trace condition, and then we consider the field equation of the theory, the field equation in that case will imply some field equations. They imply also the mu psi, of course, dressed, because we are dealing now with the dressed quantity, so psi mu equals 0. While if we take B and we look at the dynamics, the field equations will imply a weaker condition than the gamma trace. That is d slash gamma mu psi mu equal to 0.
Sorry.
Yes.
So you are claiming that if I take the original action or Lagrangian,
Yes.
I perform this transformation with this U, which is non-local.
I perform a dressing view and a local dressing, yeah.
Okay. If you want field definition.
Not
taking a psi and
exactly,
calling
but okay, if you want to call it the way you want, but that's the point that you follow this prescription, okay?
Okay. But in the end, it amounts to taking psi and calling it psi U with that definition and U non-local.
Yeah, you have to check the degrees of freedom that you are taking to do this redefinition transform that way, but okay, you are doing this.
I'm just concerned with the Lagrangian. At the level of the Lagrangian, you take the Lagrangian, you redefine the field in this way with U non-local, and you are saying that the equations of motion should not change because we are saying that this redefinition just amounts to a boundary term. So if this is true, then the equations of motion should be the same, right?
Yeah.
Have you checked that this is true?
Yes.
Explicitly.
Sense. Yeah.
Because in
Explicitly,
all examples that I know,
yeah.
all examples, I checked many of those, and in all examples, the equations of motion that you derive from the transformed Lagrangian do not coincide with the transformed equations of motion. In every example that I considered, this is not the case. So even a complex scalar in one dimension does not satisfy this property. So I'm very
gauge covariance?
Sorry?
Gauge covariance? This is
I
automatic. I mean, when you have a Lagrangian and you gauge transform with a boundary term, the field equation written in terms of the new variables are exactly the same as the equation written as the old variable. It's
but
gauge
you
covariance.
cannot discard the boundary term if the transformation is not local, because the boundary term is not bounded.
Okay, here we are. Okay, wait a minute. Here we are making some confusion. So let's try to go straight. First, you get the same functional expression for the field equation, so same covariance space of solution is preserved, but here you have the dressed field appearing in this functional expression for the field equation. So if you say they are the same, it depends what you mean with the same, first of all. Secondly, we are in cases in which you consider the theory to be in the presence of a non-trivial boundary, so when you vary with respect to the field, you have those terms that are d of something delta of the field, so you still have those boundary terms. This still can be solved via dressing, but it's another thing. It's how the boundary problem, according with what we have seen now, is not only solved but dissolved, both technically and conceptually, via the dressing. But that I agree that in principle you have to be careful when you vary explicitly with respect to all the field to what you get in the boundary terms. So that I agree. But regarding your question, they have the same functional expression, this we checked, of course, for the dressed object. If you want to write them in terms, if you want to unfold it, you will have precisely a boundary term.
So
With bare plus a boundary term in the field equation, boundary term that is particularly is non-trivial because it is expressed as also the contraction along the dressing field of the field itself. So it's non-trivial the way in which they
and it could be
change
non-local,
the
I
respect
guess.
to the variable.
If
It
you
will be
express,
one under locality because the dressing is non-local, yeah.
So if you express this E of U in terms of the non-dressed fields, this thing will be non-local.
Yes, you will, okay, you will have the dressing is non-local, then of course there might be combination in which localities, that it depends
Yes,
on
of
the main
course,
model.
it might be.
In which it might be, but maybe you will still have it, yeah, sure.
Okay.
Yeah. And okay, so just to be quick and come to the thing I want to mention about unconventional supersymmetry. So at this level, take all what we have done till now and think of generalizing to supergravity, of moving on to supergravity. So what you do is that you replace, we know where is it? Okay. You replace so super quick. You replace D with the covariant derivative. You replace gamma mu with gamma A E A mu. And then you do the same construction at the infinitesimal level, at the perturbative level, it works well. Of course, if you want to construct it in a fine way, you need more mathematics, essentially more bounded geometric framework and maybe generalized theory of the derivative and so on, because in particular we know that supersymmetry transformation in superspace, they are diffeomorphisms along the fermionic direction, so it's more complicated, the treatment. We have done this in supergravity at the perturbative level in the paper, so and it follows, apart from the fact that you consider the infinitesimal transformation, it follows exactly the same prescription with just the gamma and the covariant derivative with that. You also dress, you have also the spin connection now and the field band, so you dress also them. And when you write the Lagrangian, you have in the simplest model, you have the Einstein-Hilbert plus Rarita-Schwinger term, you dress the theory, and you can get also more complicated cases in the supergravity realm, say. What is interesting at this level is actually in the appendix of this paper on supersymmetry and dressing is the fact that, okay, one may say, but I have a geometric framework, that is the Relational one, where to apply where supergravity is constructing the probably most geometric way known to now, let's say. So, and we have super bundle structure, so what I would want in that context is to try to build a dressing superfield and to dress concerning. So essentially you take the gravitino as a superfield, as one from superfield, and so you split it into dx and theta direction, and you do the same for the dressing, and then you just check if you get the dressing superfield, and then you check that the restriction on space-time give what you would get at the perturbative level, give what you would get via perturbative dressing of the theory on space-time. Okay. So, while these are for supersymmetry and supergravity, regarding unconventional supersymmetry, what we wanted to check there is if the matter ansatz can be seen as addressing, and in fact it is not again a gauge fixing, but it is addressing. In which case, okay, first of all, about unconventional supersymmetry, we have to say that it does not require, it's freer as a framework because it is not a true supersymmetric framework in the sense that you don't require the matching of bosonic and fermionic offset degrees of freedom. The only thing, and also the aim is different because in supersymmetry we want to unify spatial, temporal, and internal symmetries, while for unconventional supersymmetry, in principle, what you want to do is just give a unified description of fermionic matter fields and bosonic gauge fields. And so you exploit what of supersymmetry just as a supersymmetric framework, the supergeometric framework. You use a superconnection. And in doing so, during that, so we can consider, we have considered the simplest, the original model in which unconventional supersymmetry was introduced, that is the AZ model. Alvarez Valenzuela model in 3 dimensions. And actually, since the dressing starts from some kinematics and then we write the dynamics, we always follow this prescription, this procedure. We have also understood how to extend this unconventional supersymmetry beyond what it was at first originally introduced for, so how to extend it in higher dimensions, and also how actually this is generally the dressing, or this dressing procedure in which, by means of which we get to the matter ansatz, does not depend on the amount of supersymmetry, on the dimension, on the dimensionality of the theory, so on the space and dimension. So, but let's consider the model that we know the best for doing this. So we start from this AZ model is based on H, that is OSP 2, so gauge group OSP if you want to do, and gauge superalgebra and so on. What we are interested in is so the gauge. Let me write the gauge algebra is let me call them the parameters lambda and the prime. This is from you to H algebra, and so these such that they transform as delta lambda prime is the adjoint, and so it's the commutator lambda prime lambda. Same, okay. So this just right in the paper we introduced a matrix notation which is very powerful to check the transformation, to write the connection, the fixed strands, to check the dressing. So, but we can also write the way in which we are used to. So I write lambda x, the gauge parameter, and I write it expanded along say 1/2 Lorentz component, Lorentz parameter, Lorentz generators AB, plus Q bar epsilon x, and then the minus epsilon bar x Q, plus alpha x T, the Newman piece. And what is important to write, that this is key to unconventional supersymmetry, is the fact that I want to write the OSP superconnection. So it's again 1/2 omega AB, say J AB, plus Q bar psi minus psi bar Q plus A T. And then accordingly we can write the fifth strands, okay? But we are using the original paper in our formulation, in our paper and so on. And then we add that we want to implement into the superconnection a matter ansatz. That is, we want to write psi as I gamma A E A chi. So this is the matter ansatz where EA is E in Dx mu. In such a way that we can write the superconnection A, the connection A in this way, AB, and then split into I Q bar gamma chi plus I bar gamma Q plus A T. And again, okay, now we don't have time, but it
Maybe
is,
we can continue another
yeah, another time, but just to come to a point of
Okay.
this construction, because it's just a matter of writing the transformation lambda in a matrix notation, which is faster to deal with and clearer to deal with, and then the same for the connection and for the fifth strand and so on. So and then again, okay, of course we know that we have the dynamics of the model, which is a Chern-Simon theory based on this supergroup, so you can write it, okay? We already know several of that part. What is interesting is the fact that now we exploit the same decomposition that we had considered before. So the point is to show that this is addressing, is a self-addressing of the fermionic one-form field appearing in the superconnection. So we exploit again this decomposition, in which, just for simply to avoid the confusion, let me call it Z, this object, because of the way in which we typically name this object in the matter ansatz. Let me call this is again the trace, the gamma trace part, the spin-1 field, and so Z is defined as minus this in three dimension. Of course, you can generalize to one dimension. You consider the gauge transformation of psi, and then you write the same transformation for those fields, for the fields in the reducible representation. So delta epsilon rho mu is third gamma mu lambda slash epsilon plus lambda mu epsilon, and we define this to be b mu epsilon. So we introduce an operator for simplicity, which we call b mu, which is minus I third gamma mu lambda slash minus lambda mu, a non-local operator which has a formal inverse that is b minus 1 mu, and we replace so this reducible representation. We can then consider addressed objects like psi mu as psi mu as the rho mu plus I gamma mu z mu. This formal in abstract, we can think of an object that is dressed this way, and then we see that if we now take as a dressing functional constraint rho mu to be equal to 0, and we solve explicitly this condition, again the same, we implement the dressing. Essentially what we get is that we obtain a non-local, again, dressing field, perturbative at this level, of course, I'm writing everything at a perturbative level. It's mu psi, and it will be b minus 1 mu precisely rho mu. This, what does it mean is that for dressing this time, again, it's non-local, and I'm using the degrees of freedom. I know that it's a bit, this is a nu, psi is the dressing, so it's b minus 1 mu, that is this non-local operator, applied, let's act on rho mu. And so this time, we are not using the degrees of freedom of the order chi. Yeah, exactly. And in this way, we get, finally, when you do the substitution, we check that the transformer is addressing, that is correct, and that the object that you get
change pen.
Maybe
Lucrezia, to the with all the blue.
Yeah.
So what they get is psi mu is I gamma mu z mu in the end, and I can call this I gamma mu chi. And so you can show, and there is in the paper, we can discuss about it, but what you can see is that again, using the Supersymmetry method, you get the matter ansatz, and you introduce a non-local dressing, so the unconventional supersymmetry, is a substantial symmetry of the model, differently from, for instance, what you can do with the nearby symmetry, in which you can write, okay, this is just to mention, you can write it in any dimension. If you focus in 2 dimensions, the object that you build in the end, so this object, which is actually a dress, the object is outside nu, is nearby in mind, but you didn't have to dress with one local field to get this kind of object. So it's just to mention a symmetry introduced from the outside with respect to the model that we are considering, and on the other hand, a symmetry that was substantive to be dressed and to make this region environment.
And the difference is that the E is an object which is outside your fields, the EA.
Well, no, actually, the EA is a field that I consider is a field that I have in the theory. At the level of a super bundle, because here the important thing also to extend to higher dimension actually you see is that size Q, so in some of the fermionic direction has to be in the fiber. They don't have to span the basis as we are used to in the real because they have to be really gauge supersymmetry transformation in the fiber. And then you may think of it with just a frame associated frame bound to the bundle in which you have E. So yeah, it's a field in the theory, is the space-time field that you're using to do this first.
So is it correct to say that in the case of supersymmetry, the price you have to pay to write everything in terms of supersymmetry invariant quantities is to have non-local equations?
Non-local objects, okay, depends on the model again, if the equation, if then the rest is non-local, but yes.
Because if you write
if you
in
qualify
terms of size, you
price,
get these non-local
yeah, at price, again, quote unquote, because, yeah, you do it, and you get non-local things, as you